Inside every major factory, power plant, and industrial facility, immense pumps push liquids across the complex. Cooling water, chemical transfers, boiler feeds. These systems are the core of production, running continuously under extreme stress, until a pump shudders to a halt. The consequences are immediate. The entire production line stops. Maintenance teams scramble to identify the failure. Purchasing managers rush to source emergency spare parts, and the factory loses thousands, sometimes millions of dollars in output by the hour. This is breakdown maintenance. It involves running equipment until it fails, reacting to the damage. It is a costly strategy that relies entirely on a lack of information. The traditional alternative is preventive maintenance. Engineers shut down the machinery on a rigid schedule, say every 3 to 6 months, to swap out components. However, this often results in discarding perfectly healthy parts purely as a precaution. Both methods suffer from the same limitation. A running pump is a solid steel block. Operators cannot see how internal components hold up under strain. The greatest threat to industrial production is the inability to see a mechanical failure coming. To gain this visibility, engineers use a digital twin. This is a live, continuously updating virtual replica of the physical machine. It mirrors the exact state of the equipment on the factory floor in real time. To build this replica, the physical machine needs a way to communicate. Technicians install a network of sensors directly onto the hardware, creating a digital nervous system. These sensors capture variables that remain invisible to the human eye. They monitor microscopic physical vibrations, track internal bearing temperatures, measure liquid flow rates, and record the motor's electrical current. The sensors continuously route this raw operational data through local programmable logic controllers, or PLCs, straight up to a centralized cloud server. Bridging the physical and virtual worlds allows the pump to report its own real-time health, revealing internal wear that was previously hidden behind solid metal. Collecting millions of data points is only the first step. For this data to be useful, an AI system must analyze the stream for specific anomalies. This chart shows how the AI establishes a baseline of health. For a specific pump, the system learns that normal operation produces a steady vibration of 8 millimeters per second. When the data shifts, the AI notices. Over a single week, the system detects the vibration incrementally creeping to 9, 10, then 11. The AI identifies this pattern, calculating exactly when the trajectory will cross the mechanical failure threshold. The system provides a specific instruction. Instead of a vague warning light, it notifies the engineers that a specific bearing will reach its failure point in exactly 20 days. Pairing live data with AI pattern recognition allows a factory to replace reactive emergencies with a maintenance schedule based on mathematical certainty. Armed with a 20-day warning, the engineering team procures the exact spare part required. There is no scrambling for parts or overnight shipping fees. They schedule a planned shutdown. During a brief, controlled maintenance window, the failing bearing is replaced. The factory avoids the losses associated with an unexpected breakdown. This technology is accessible to smaller operations as well. Even older factories can set up a limited AI dashboard by attaching basic temperature and vibration sensors to their most critical machinery. This monitoring framework is expanding across the industrial ecosystem. The same logic is being applied to industrial boilers, high-voltage transformers, and entire production lines. In a fully digitized Industry 4.0 facility, managers track the real-time health of an entire industrial complex through a smartphone screen. Manufacturing becomes more resilient when engineers monitor digital ghosts to ensure the physical machinery never stops unexpectedly.